Hi there. In this video, we will overview how to use the CORHEL AMCG interface to study and model solar eruptions. When you first load up the interface, you will be taken to this page. This is the Run Request Selection landing page. On this page, you will enter some identifying information and a run request number. The combination of today's date, your email, and the run request number are used to create a unique session behind the scenes that will keep track of all your selections and background computations. If at any time you want to completely start over, you can always navigate back to this page using this menu here on the left and enter a new session ID. That would be here. As will become clear later in this video, we also allow the user to restore a previous interface session. This is done by uploading a save set file that you can download at various stages throughout this interface. This will allow you to return to a particular setup or simulation at a later date, including changing a parameter or two for subsequent experiments. In this video, we'll assume that I'm starting from scratch on an event that I wish to study and model with CORHEL AMCG. In that case, I enter my information and select a run request number, and then we'll continue. And I hit 1 here because this is my first session of the day. So I put 1, and this can be any number up to 100 or so, I think. And then I hit next. Now we have arrived at the main navigation page of the interface, the step overview. This page briefly describes the different activities required to set up and design a full sun-to-earth CME simulation. It is also the entry point to all of these different steps, so you return here several times during a session. If you ever want to return to a specific step, you can always use the navigation menu on the left and select Step Overview. Starting off, we see that there are 4 steps on the Step Overview page. However, steps 2 through 4 are grayed out. This is because the first step of the process is map selection. Here we will select the date, time, and source regions of the eruption or eruptions that we wish to model. We call this step map selection because a key part of this process will be selecting and viewing the full sun magnetic map that will be used as the boundary condition for the MHD model calculations. To begin, we click Enter Step 1. On the map selection entry page, we first see 2 options. We can either load a map from an existing background simulation that has already been run and uploaded to the interface, more on that later, or start fresh with a new map obtained by selecting a date, time, and data source. I will illustrate both of these options in this video, but here we will start with the option to create a new map. Now we see that the text at the top of the screen has changed, and a date selection box, along with source selection options, have appeared. It is worth pointing out now that essentially all of the interface pages will have this blue text at the top. This will overview the purpose and contents of a given page. Generally, there will also be these info tooltip buttons at various sub-elements on the page. I won't cover all of these here, but typically you'll want to examine these tooltips for more information. Now I will pick a date. For this example, I'm interested in the 2 large CME events that occurred in rapid succession on March 7th, 2012. So I click these spinners here, go to 2012, March 7th. I can also use this little date slider to pick an hour of the day. This is in UT time. So I'm going to go all the way down to 00 because that's about when the flare was. You can also manually type in this box, but I'm using the spinners in this example. This start time will be used for all subsequent simulation diagnostics. For most cases, we recommend picking the time just prior to the main flare onset in an eruptive event. Next, we can use these radio buttons to select a map source. For most cases after June 2010, we'll want to use HMI. This is the magnetograph aboard the Solar Dynamics Observatory. But depending on the case that you're interested in, you may want to use another source, such as MDI, for something during the SOHO era. The info buttons indicate the approximate time range of the available data. Lastly, one can also upload their own full sun map by clicking this user button. Currently, this requires a special HDF4 format, so please contact us if you are interested. In this case, I will choose HMI and click Next. At this point, the interface obtains and plots the full Sun HMI synoptic map for the corresponding Carrington rotation that spans your time of interest. This is 2122 in this case. As you can see, there are several active regions on the Sun at this time. This is an interactive plot designed for region selection. If you click on the map, you can begin drawing a box to identify a region of interest. This region of interest will define the CME source region in the simulation, and this is where you will design and place your magnetic flux rope. In this case, I know which region was the source for the two large CMEs that occurred on March 7th, 2012, and I'll outline it here now. Generally, to know where to put your region, you'll need to look at data or movies for the event. Typically, I'll use JHeliaViewer or some other data browser to examine magnetograms of the source region near the time of eruption. In the case of JHeliaViewer, there is an option to overlay the grid in Carrington coordinates. This is the frame of the map that is displayed here. These are longitude and Carrington coordinates. If you have a particularly strong or weak region, you can also change the scaling of the map by scrolling down a bit and changing these buttons. In this case, the active region is very, very large. So I change the scaling and I select just the magnetic flux that I think is involved in the eruption. Now that I've selected a region, I can scroll down a bit to change some options and select a second region. In the elements below, we see the name of the region, as well as some tabs. The AR Selection tab indicates numerically our region selection. This can be used to manually enter or fine-tune the selection. In the Mesh Resolution tab, these gray boxes roughly indicate the number of points required to resolve the source region at high resolution. Typically, the defaults work just fine, but I will enter a new, slightly smaller number here as an example. Although the final resolution of the MHD calculations are set largely by your flux rope choices, entering a larger or smaller number here will control the smoothness of the active region into which you place the rope. As a rule of thumb, anything less than 70 points across will run reasonably fast in the interface. Next, one can optionally name the region to something memorable to facilitate interface navigation. Here, I'll be creating two CMEs from the same region, so I'll name this one after the first eruption, which goes to the northeast. Now that I'm happy with this, I will click Save so that the region selection and parameters are remembered. If I were only simulating one CME, I would then click Next to move on. In this case, I will click the plus button to build the region selection for the second CME. In general, we can pick a region at any location on the map. The second region could be here, or it could be here, or it could be here. Of course, this would depend on your circumstances. But in general, simulations with two regions that are far from each other in either longitude or latitude will require more time or computational resources, because the model grid will need to resolve both of them at the same time. In my particular case, though, the second CME erupted from the southwest portion of the same active region, this one right about here. So I will select a smaller subregion of the original one. At this point, I can also tweak the parameters and give it a name. MFR2 Southwest. When I am happy, I can then go and click Next. As you can see, we have now returned to the step overview page. However, now steps 2 and 3 are available. At this point, we can either design our magnetic flux ropes and create a zero beta simulation, that would be step 2, or set up a thermodynamic background simulation, that would be step 3. At this point, it's really up to you what to do next. The full physics thermodynamic CME calculation is step 4, and this requires that both have been done at some point. So, if you just want to play with building flux ropes first, then select step 2. If you want to get the background run started and running in parallel, say, on the supercomputer, then select step 3. In this example, I'll start with building my flux ropes by clicking Enter Step 2. On the first page of Step 2, we see a list of regions that we created in Step 1. Clicking on a region name will take us through the flux rope creation process. We will repeat this process for both regions. I'll start with the first region. On this next page, we will select the portion of the polarity inversion line along which the magnetic flux rope will lie. When we first click into this page, a 3D potential field is computed in the background. This may take some time to finish depending on the size of the region. Once the plot loads, we should see a series of lines overplotted on the magnetic field map. Each of these lines indicates a contour of BR equals 0 at different heights in the source region. These are known as polarity inversion lines, or PILs. The idea of this page is to select a segment of the PIL that roughly spans where the flux rope should be placed. This information is then used to create the initial guess for the flux rope axis path and for some of the force diagnostics on the subsequent page. Scrolling down, we see a number of boxes and buttons. Here, one can adjust which PIL lines are displayed and at what heights they are taken. This black line indicates the selected height that will be used when we click on the map. Generally, the higher up the PIL, the smoother things get as the field simplifies with height. Since flux ropes lie slightly above the photosphere, it often makes sense to choose a PIL height around 1.01 or so, which is the default. Depending on the case, you may want to go lower or higher. We can change the default PIL selection by clicking the focus button as we see here. This is a higher height or smoother line. This is a much lower height, the photospheric height, which is a more complicated line. I'll go back to the default now. Since this is a relatively strong active region, another thing we can do is change the scaling of the image to bring out the stronger fields a little bit better. I do this by clicking on this AR Image Scaling tab and entering a larger number. Now I can select a PIL segment by clicking on the map. The idea is to roughly span where you want to place the rope. For this first rope, based on observations, I suspect that the negative footprint is roughly over here. I think the positive footprint is roughly over here. I want the PIL selection to roughly connect to these places. When I click the first time, it will find the nearest intersection of my click to the PIL. This is indicated by the yellow point. When I click the second time, it'll again find the nearest intersection and then find the shortest line connecting these points. This will define the PIL segment, which is shown in green. I can tweak the PIL selection by clicking again, and it will update the point nearest to the click. Once I am happy with the PIL selection, I can then click Next. We have now arrived at the most important page in the interface, the flux rope design page. Here we will select the footprints of our flux rope and play around with the axis geometry until we are happy. Before launching into the demonstration for this example, though, it is worth pointing out that this is a complex page with lots of features. For this reason, we have included a lot of helpful information on the page to help guide you through it. First, we have the basic instructions for how to build a flux rope in this blue box at the top. We also have this tour feature that will give a high-level description of each sub-element on the page, and I'm stepping through that now. This can be useful for figuring out what is what and where you might find things on this page. Lastly, the majority of the important parameters or options for building a flux rope have an additional tooltip. This will provide very specific details on each one of these parameters. Of course, like all things, the best way to learn is by doing. Once you start playing around with the case, build some ropes, and run some zero-beta simulations, you'll start building some intuition as to how it all works. Don't worry about making mistakes for the first time. So the first thing I will want to do is pick the footprint of the flux rope. This is where the axial field and electric currents of the flux rope intersect the photosphere at both legs. We will need to click on this left map twice. The first click will always be assumed to be where you'd like the positive footprint. The second click will be where you want the negative footprint. Generally, the rope footprints will be at or near the relatively strong fields and at or near the PIL. Here, I know roughly where the feet should be based on the observations and coronal morphology of this event. So I'll click once here and click once here. Once we have clicked twice, the interface will populate the map with an initial guess. Here we see several things. The circles around the footprints indicate the diameter of the flux rope body, and this red curve is the axis path. These blue dots with arrows sticking out of them represent the spline knots that are used to define the axis path. At each of these locations, we also compute the local magnetic forces and average them over the flux rope cross-section. The strength and direction of this force is indicated by these blue arrows, which can help visualize what the rope might do once you place it. On the right-hand side, we see another 2D plot illustrating additional aspects of the flux rope geometry and magnetic forces. Here, we have a special projection in the plane defined by the horizontal path of the flux rope. The x-axis is the projected length coordinate along the rope. Starting at 0, we have the negative footprint, which is on the left, and we end on the right with the positive footprint. This y-axis is the radial coordinate, which indicates height above the photosphere. Similar to the plot on the right, this central line with dots on it indicates the spline locations, forces, and the axis path of the flux rope. These thinner pink lines, above and below, indicate the width of the flux rope in height. The colored contours in the background of this plot are contours of the external potential field that is normal to this axis plane. This is essentially the strapping field that can hold the rope down. This is also called sometimes the external poloidal field, or BP. Looking at both of these plots, we can get a nice sense of the 3D flux rope geometry and the external magnetic field distribution. Looking at these forces, we see that some of these arrows are up and some of these arrows are pointing down. Some are also side to side. This is typical of an initial guess, which is made by the interface once the footprint locations have been defined. Now that we know how to pick a footprint, and now that we know what is shown in these plots, we can start playing around. Scrolling down, we see a bunch of information in a table here, and we also have a bunch of tabs that will allow us to define various flux rope properties. The first thing we can do is change the width of the flux rope. This is defined by the minor radius box shown here. I can make the rope slightly thicker by entering a larger number, and then I can make the rope slightly thinner by entering a smaller number. Typically, the thickness you will choose may depend on the specifics of the case, so it always helps to watch the observations. For example, by looking at the EUV imaging data that's available in something like HelioViewer. One helpful guide, though, in this interface is the fluxes presented in this table above. The top row, right here, shows the integrated flux of the magnetogram in the entire region of interest. This next row shows the magnetogram flux within the circular footprint of the RBSL rope. So this is smaller, but still a significant fraction of the total active region flux. This next row here shows the axial flux of the flux rope, and the row after that shows the ratio of the rope flux to the magnetogram flux in each footprint as a percentage. I find this last row to be particularly helpful because typically my first aim when building a rope is to find a configuration that is close to the marginal stability point. In this case, you'll generally want to balance the flux between both polarities, so equal ratios, and not greatly exceed the fluxes that were present in the map, say a factor of 100%. In this case, I see that I have a slightly smaller rope flux than my magnetogram flux, and it's not perfectly balanced. This can change, though, if I move the positive footprint slightly, which I can do by clicking on this orange dot and moving it slightly to the left, away from the stronger polarity. As you can see, every time you move it, it will update. And now my ratio is closer to 1:1 and still relatively small. Now the next thing we can do is adjust the relative strength of the flux rope, which is controlled by the axial current flowing along the rope. While the axial current is formally a free parameter, appropriate values for the current will generally depend on the strength and properties of the external field in the region of interest. In the interface, once we have a given flux rope geometry, an optimized current value is computed automatically behind the scenes. This is the value of the axial current that will minimize the relative strength of the magnetic forces with respect to the relative strength of the combined fields. The idea here is that this value should typically give a stable flux rope configuration. Once we know this value for optimized current, we can then multiply it by some factor to achieve the desired result. And this factor is what is set in the interface. For example, here the fractional multiplier is 1, and the axial current in the gray box is about 10.7, which represents the optimal current if the factor is 1. I can make the rope significantly stronger by using 1.5 or 2 in this box. Notice how the strength and direction of the force arrows change with this choice. For 1, the arrows were mostly pointing down or side to side, and this rope was likely stable. For this 1.5, they are mostly pointing up, and this rope is likely unstable, as in it will erupt. Generally, the stronger the current multiplier, the stronger the eruption. Put 2 in here. So, if your goal is to find the threshold value of current between a stable and unstable state, then you can vary this fraction progressively over a series of runs to find that value. Another thing we might want to play with is the shape of the flux rope axis and height. That's this curve here. We can do that by going to the Axis Modification tab. The most important parameter is the base height, which sets the maximum height of the flux rope axis. As you can see, it's set to 0.025, and our maximum height is around 0.025. But we can move this rope up or down by adjusting this parameter. So here I'll go slightly lower down. Generally, a lower rope will have stronger fields because the axial current is sensitive to the external field, which varies with height. And we can see this by going back to the Flux Rope Properties tab and seeing that the axial current has increased. Back on the axis page, the top 3 boxes, these ones right here, can be used to fine-tune the height profile along the length of the rope. I can change the relative peakiness of the height profile by changing the width of the peak and the amplitude of the peak. We'll do that now. And I can change the relative position of this peak along the length of the rope, normalized to 1, by changing this position of the peak thing here. And so now we see we have a very low-lying rope with a sharp increase here. In general, you'll want to roughly match this shape with the contours of the external field in the background of the image. But it doesn't have to be perfect. And as we can see here, I'm largely missing this contour over here, and it looks pretty ugly. So I'll go back to the defaults. In this case, I say that these contours are roughly symmetric along the flux rope axis, so this is not too bad already. I can make it slightly wider, and I think I want to raise the flux rope just a little bit so that the bottom of the rope is not quite intersecting the photosphere. If the rope is intersecting the photosphere, then sometimes the line tying effect can keep the rope down. At this point, I can go back to the Flux Rope Properties tab and stare at my plots to decide if I'm happy with my flux rope. Thinking back about my knowledge of this event, I know that I want to put a second flux rope right about here, and that maybe my negative footprint was roughly here, and my positive footprint maybe up here. So if I want to tweak my flux rope selections, one thing that I can do is either start changing these numbers or moving things around, or I can start again from scratch. I'll show that right now. Here I hit total reset, and we can see that this plot has gone away, and I'm starting again from scratch. So I can put my positive footprint now somewhere up here, and my negative footprint now somewhere up here. And again, I have a flux rope built by the interface. We also see that my width of peak, base height, and miter radius choices are also reset when I've done this. So I'll start playing with those again. Now I see that I still have roughly equal balance of my positive and negative footprint, but a slightly lower axial current than I had before. For whatever reason, that has to do with the force balance between the current carrying body of the rope and the external field. If I want to bump the currents back up again, I can increase this number a bit, and we should see these arrows start to rise, telling us that the forces are getting bigger. I can also go back to this axis modification and decide, well, maybe I want to bump up the axis a little bit more. So I'll do maybe 0.5 again, and maybe a base height of 2.2. Go back to my flux-rope properties page, and I can see that I have slightly more current than in the case that I had illustrated before. So at this point, I can decide, well, let's see what happens. And for that, I'll then hit Next. Now I'm back at the source region navigation page. I've completed setting up the first rope, so it's green. But I've not designed the second rope yet, so it's red. Both of the ropes, or as many regions as I've selected, will have to be designed before we can create the zero beta run. I'll breeze through the design of this second rope now. At this point, it's computing a potential field solution for the next region, the second region that we had selected. And this will take a second generally. And again, we see that we'll be on this PIL page, and we'll get to pick a certain height of the PIL and a certain segment. But now we see that it's very much zoomed in because this was a smaller region of interest focused right on this second flux rope position right here. I think I'll stick with this radial height of 0.01 again and click close to the edge here and maybe close to the edge over here. Now we see this zoomed in little cutout of the region. The image scaling has reset again. I think I chose 1,000 last time. Maybe I'll choose 1,500 because this is a pretty strong patch. And I think I want a positive footprint right about here and a negative footprint right about here. As we can see, the default size of this is now looks slightly different because this region of interest is a little smaller. So I'll move this footprint here, move this footprint a little further away, and now we see that we're starting to get a little more balanced again with the positive and negative flux. Right about there. One thing we do notice is that there's this sort of sharp turn in my flux rope right here. That's because the automatic generation of the path wants to snap to the PIL, smoothly go to it, and then go to the right footprint. If I don't like this, I can change the PIL segment that I've selected. So I'll go back and show how that works. Because it's already computed the potential field, this step is quicker. I then click a bit further in for the neutral line segment. And we see that now I've selected a smaller little piece of that. And now I click Next. And it looks like what happens is it remembered the old geometry. So I think I hit this Clear Footpoints button. And I'll click again and again. And now we have a nicer little connection here. Fantastic. Now we see that this is a little more peaked. This might be overkill given the relative crudeness of this whole approximation, but we can make this a little smaller and a little bit more peaky, like so. And now you see that it's roughly following the shape of this contour a little bit more, but I don't really want to add too much curvature to my flux rope, so I might stick with this. Might bump up the fraction of optimized current a little bit as well. We can see these arrows are maybe roughly side to side, some are up. Go a little bit higher. and we'll see what happens. Now, I'm actually doing this blind. I've not really played with this case very much before, so it could very well happen that this flux rope is a little bit too high and a little bit too compact for this region. So I can make it a little bit smaller though. Fantastic. You can see that the axial current of the second rope is slightly smaller than the axial current of the first one, which is consistent with my impression of the observations for this particular event. Now that I'm happy with this rope, I can click Next again. At this point, we see that both the first region and the second region are green, and now a Next button has appeared. This will take us to the zero beta summary page. At this point, the interface has enough information to create the inputs and input file for the zero beta run. Currently, this is done by creating an archive file that can be used by CORHEL to launch the run. After a few seconds of landing on this page, a top button will appear. Clicking on this will allow you to download a tar file that represents the run archive. If you have access to a CORHEL installation on a computing facility, just copy this file over there and follow the CorunPy launch instructions to start the run. If you are using this interface for runs on request at the CCMC, then you should be able to just submit the run at this point. Below the archive button, we see some basic information about the run size. This first row shows a typical zero beta run size, while the second row shows the current zero beta run size, based on your selections. There's also a column for the number of processors, which can be used to estimate the average runtime. In this case, we estimate about 27 minutes on 192 processors for this run, or about 11 minutes on 480 processors. Now, one of the most important features is down right here at the bottom. This is a button to download the interface save set. This is a lightweight tar file that contains all of the information you have entered into the interface so far, including the flux rope parameters. If you ever want to reproduce this session, or go back and tweak a parameter or two, such as the flux rope currents, you just have to upload this file by selecting it on the start page of a new session, and you're back to where you started. Now that we have set up our zero beta run, we can hit Next.